All right, next our discussion is going to be about polarity effects on solubility. So by looking at a molecule and determining if the molecule is polar or nonpolar, we can predict the polarity of the compound. All right. Something that usually people learn somewhere along their chemistry careers, that like dissolves like. All right, which basically means that if you have a compound that's polar, it will dissolve in a solvent that's polar. So for example, sodium chloride is very polarized. It's ionic, has a sodium plus and a chlorine minus, so it will dissolve in polar solvents. One of the most polar solvents is water, so that's why salt dissolves in water. Okay, and then the opposite is true. Nonpolar dissolves in nonpolar solvents. So nonpolar compounds dissolve in nonpolar compounds. That's why oil and water don't mix. Oil is very nonpolar. Water is very polar. You have the two layers. No matter what you try to do, they will not dissolve. As far as nonpolar, this is just kind of an everyday thing to kind of know. WD-40 is one of the best solvents to use, especially if you have a kid. If you got a kid, they write on everything. They use markers, they use crayons, everything in your house. Anyone that has parents knows exactly, anyone that is a parent knows exactly what I'm talking about. WD-40 is, it's used to lubricate, things, but actually it's a great solvent to have around the house in case you have something that won't dissolve. It's actually pretty good as a cleaning product on pots and pans if you're trying to get a lot of stuff off. So that's just kind of an everyday thing, just to kind of know that WD-40 is kind of a mild organic solvent that's actually pretty useful to have around the house. FYI. Also, what this actually, if you break it down to the level of the molecules, that molecules with similar intermolecular forces will mix. So if you have something that only has London dispersion forces, you'll want a solvent that just forms London dispersion forces. If it forms hydrogen bonding, all right, if you have a solvent that does hydrogen bonding, it's not going to mix very well with things that just have London dispersion forces. Okay, now it's not. There's kind of gray areas. Like if you have something that's a dipole and a solvent that's hydrogen bonding, it could mix. Like for example, alcohol mixes pretty well with with water. You can mix alcohol and water, no problem. But at a certain point, if you add too much alcohol, it won't mix anymore, because your water has so much hydrogen bonding, where your alcohol has a very few amount of hydrogen bonding, that once you quote unquote saturate your water, you're not really going to form. It's not going to be soluble anymore. Okay, so just kind of a good rule of thumb is that if you have similar intermolecular forces, they will be polar. All right. Now I want to show a demo in class. I might forget, so remind me in class. Say, Dr. Steve, you said on your videos you're going to do a really cool video that shows like dissolves like. Okay, it's a really cool demo, so make sure you remind me, otherwise I'm going to forget. Okay, so in this slide you can see polar solvent. A polar solute in a polar solvent. It's the exact example I gave you. Imagine this is sodium chloride. All right, you got very highly charged molecules. Water, very polarized, partial positives on your hydrogen with a big partial negative on your oxygen. So the negative portion of it will be attracted towards the positive part. So you can kind of see if these are your oxygen molecules. These kind of look like Mickey Mouse molecules. But imagine that's water. Your partial negatives attract to your positives, and your partially positive hydrogens are attracted towards your negatives. Okay, so a polar solute dissolves polar solvents. The hydration releases energy. All right, your entropy increases. Remember from Chem 2, entropy. All right, our whole universe is always in an increasing state of entropy. That's what we want. Here's a perfect example of a polar solute with a non-polar solvent. So imagine I take water and throw it into oil. Well, this is kind of salt. So imagine I take sodium chloride and throw it in vegetable oil. All right, let's just call this oil. What's going to happen? Yeah, your salt's not going to do anything. It's just going to fall to the bottom. All right, because your vegetable oil does not want to interact at all with this. Highly charged. It's pushing all these molecules away. Okay. So here's nonpolar. Here we have, imagine you have a kid that has a crayon right on the walls. Crayons are wax. All right. So imagine this is your crayon, and this is your WD-40. Great way to clean up your crayon on the walls or on the tables or on the floors. All right, or on your computer screen. Thank you very much to my kids. I had to clean my computer screen a few times. Which is, if you think about it, it's pretty ingenious. A kid sees a picture on the computer and he thinks he can color it. Hey, I'm not going to hold that against him. He's thinking, don't write on Daddy's computer, please. Okay, so you got the wax, you got your nonpolar solvent. They are going to mix. Very similar intermolecular forces. These are London dispersion forces. So perfect interactions. All right. Here's again a perfect example of oil and water. So imagine this is the oil right here. Here's the water. All right, perfect example, oil and water. Nonpolar molecule is not. What would have to happen is these molecules would have to break up all of the hydrogen bonding, which is not going to do because these want a hydrogen bond, and you don't have hydrogen bond on your molecule, so it's not going to happen. Okay, so that's like dissolves like. The next topic I want to talk about are the classes of compounds. And you know what? I am actually going to end the video here, and we're going to start a fresh new video on these classes of compounds.